Hello everybody, great to join you. Today I'm going to talk about emission scenarios consistent with 1.5 degrees of global warming, and I'm going to focus on carbon dioxide removal. And the scenarios I'm going to use are based on the IPCC 6 assessment report, the Working Group 3 part of that report, which was published around about a month ago. So first of all, I'm going to go straight to showing a few scenarios and talking through those. So this figure here shows global CO2 emissions in a set of 1.5 degree scenarios, those that have no or limited overshoot. I'll mention what that means in a minute. On the vertical axis here, we have global CO2 emissions, and on the horizontal axis, we have time. The black here is emissions that have already occurred, historical emissions. So there's about 100 scenarios in this figure, and they all have generally the same characteristics. There's a peak in emissions, which needs to happen pretty much immediately, as soon as possible. After that, there's a rapid decline in emissions, and they reach net zero CO2 emissions around about 2050. You'll see here that some scenarios reach net zero CO2 emissions a little bit earlier, some a little bit later. Then after they reach net zero CO2 emissions, they go net negative. So on a net basis, carbon is being removed from the atmosphere overall. This is a 1.5 degree scenario with what's called no or limited overshoot. So this means that the temperature in the scenario increases, gets to around about 1.5 degrees or maybe up to 1.6 degrees, and then comes back down below 1.5 degrees. And these negative emissions after net zero, they're helping bring that temperature back down. There are other scenarios which have 1.5 degrees with high overshoot. They might go up to, let's say, 1.5 degrees before coming back down. They probably, in most cases, require a little bit more carbon dioxide removal. And you can also look at, for example, 2 degree scenarios. The 2 degree scenario would look very similar to these scenarios here, but the net zero year would be shifted to, let's say, around about 2070, meaning the rapid decline in emissions after the peak is slightly lower, still quite rapid. So this is the sort of global picture looking at aggregated total CO2 emissions. In the next figure here, I want to pull that apart a little bit. This is a figure that's coming from the IPCC assessment report in a box on carbon dioxide removal. It's showing total greenhouse gas emissions. We've taken the vertical axis off here, so there's no numbers, so it could represent a country, if you like, not just the global emissions. And I call this figure the anatomy of scenario. We're trying to show the key components in the scenario and how that works. So if you look at the top part of the figure, the brown, grey and the orange, these are deforestation in brown, fossil CO2 emissions in orange, and in grey, and in orange non-CO2 emissions, things like methane and nitrous oxide. In a 1.5 degree scenario, generally you'll see they all go down quite rapidly, but they don't reach zero. So in the middle of the figure and towards the end of the figure, you see in particular fossil CO2 emissions continue, as do non-CO2 emissions. And this is essentially why we use or see a lot of carbon dioxide removal in these scenarios. So the green at the bottom here is carbon dioxide removal. We've put some emphasis here on the dark green, which is removals coming from managed land. Could also be coming from afforestation, but also forests that are just standing there taking up carbon. This is already seen in many countries' emission inventories, and we've tried to emphasize that today we already have some level of carbon dioxide removal. The light green out towards the second half of the century there's other types of carbon dioxide removal, those that we don't really have much of today, such as bioenergy with carbon capture and storage, direct air capture, soil carbon, and so on. So now, as I mentioned, the CO2 emissions and the non-CO2 emissions don't quite get to zero in these scenarios, even though they decline rapidly. And therefore, carbon dioxide removal is used to offset those emissions that don't go to zero. So why can't we get emissions to zero? You could think about, maybe long distance transportation still has some emissions. Chemical production might still have some emissions. Steel production might still have some emissions, or they might be very costly to reduce emissions, in which case it is seen in the model, at least, that it's cheaper to emit and then remove that carbon back out of the atmosphere with a different technology, carbon dioxide removal. In the agriculture sector, where you have methane and nitrous oxide, it's very hard to decarbonize those, probably can't get those emissions to zero, and you might use a level of carbon dioxide removal to help offset those emissions. Moving out to the second part of the century here, from 2050 onwards, or after net zero, you'll see all these scenarios here, or this illustrative scenario here, I should say, goes net negative. So the black line and the black dotted line both go below zero. So carbon is being removed from the atmosphere, and that brings temperature back down from a peak, as I mentioned in the previous slide. So the main interest here today is on the carbon dioxide removal. So I'm going to talk a little bit more about the bottom half of this figure, the green parts. How big is that part of the figure? So this figure here shows carbon dioxide removal in those scenarios that I showed in the first slide, 100 or so scenarios with consistent with 1.5 degrees with no or low overshoot. And the numbers here are quite large. There are some challenges in estimating these emissions. I'll talk about that on the next slide because of different definitions with different variables and different types of carbon dioxide removal. But the scales here are large. So to put some perspective on the scale here, if you take let's say a coal power plant and assume that it's using biomass and with carbon capture and storage, so a bioenergy with carbon capture and storage facility, or you take a rather large direct air capture facility, one that we have not remotely seen around the world, but let's say takes up about 1 million tonnes per year. So I'm taking here 1 million tonnes per year removal at a facility as sort of an average large scale facility. Then you would have to build one of those every week out to 2050, and you would get to 1.5 billion tonnes per year. That's much lower than the median here in this figure, which is 5 billion tonnes a year. So to get to 5 billion tonnes a year, you're talking about building several of these large scale facilities each week out to 2050. So these numbers here are immense. Moving a little bit more into the different technologies here. So this figure has 4 different types of carbon dioxide removal: bioenergy with carbon capture and storage. So you grow biomass, that removes carbon, then you burn the biomass for energy, but catch the CO2 and put it back in the atmosphere. That's bioenergy with carbon capture and storage. Direct air capture is a machine, which essentially sucks carbon directly out of the atmosphere, and again, you store it. Afforestation, growing forests, and enhanced weathering, using rocks to help take up some more carbon. So you'll see clearly in this figure, most scenarios use bioenergy with carbon capture and storage. Just about all scenarios report this a variable, and it's used at scale. Direct air capture, only about 1/3 of scenarios use that technology. It's relatively new technology, so there's much more uncertainty about its deployment levels. And also, if you use more of that technology, it might displace some of the bioenergy with carbon capture and storage. Afforestation, this one's a little bit more challenging because most models, and actually all models, report net land use change, and net land use change includes afforestation, but only some models, about 2/3, record this afforestation variable directly. So we don't have a good handle on the size of this removals from afforestation in total. And you'll see it starts at 0 in all these scenarios here, whereas the previous figure I was talking about, afforestation and managed forests, already exist today. So there's a sort of a baseline issue. So we need to be a little bit cautious of the carbon dioxide removal in the afforestation. And then enhanced weathering is shown on the bottom right there. Not many scenarios include that technology at all. But this gives you a sort of idea of the different technologies and how they're included in the scenarios. So just wrapping up, scenarios use large-scale carbon dioxide removal. I would argue, some will disagree with me, but I would argue that the scale is implausible given the real-world developments. Now, I expect that we would have some level of carbon dioxide removal. The question is really how much. Some level of carbon dioxide removal is likely to be beneficial. As I sort of mentioned, maybe carbon dioxide removal is the cheapest option in some sectors that are hard to mitigate, let's say chemical manufacturer, and maybe we need it to offset, let's say, fertilizer use, so nitrous oxide emissions in agriculture and so on. And an important point here is that carbon dioxide removal only really has a function if emissions are actually being mitigated. There are no real scenarios where emissions can continue as normal, and then we just use carbon dioxide removal to bring those down. We could simply never get carbon dioxide removal at that scale. So carbon dioxide removal only makes sense if emissions are also being reduced drastically. And I'll finish up there. Thank you for your attention.